Welcome back to System Software. We are wrapping up our section on processes. We learned about what a process is. It's a running program. Last time we looked at redirection, how we can use the standard I/O convention in order to abstract away decisions about I/O when we're writing a program, and then it's the parent of the process, like bash or some other program, that makes those decisions about I/O. And redirection was one thing we could do with that, one technique we could use to exploit this standard I/O. So before I begin, questions on redirection, questions on the project, which is due Wednesday, and I'll go over the homework as well, but questions about processes, redirection, I/O, fork exec. Questions about the FS project? All right, everybody's good? Okay, so let's go over the homework first. So what files are given in standard I/O? Yeah. Yeah, standard in, standard out, standard error. Good. Okay, so write a bash command that uses grep to find lines matching hello from standard in, redirected from a file called my.in. So what might this look like? Let's see if I'll make a file called my.in, kind of using redirection to do that. All right, so how can I write this program? I have grep, and I redirect the input of grep from a file. Any takers? To match lines matching hello. How should I write this? Yeah. Grep hello. Yeah, less than sign in my.in. So grep, as all of these core utils do, or these common utilities do, is they just read and write from standard I/O. So they don't make any decisions about which file or which device to read or write from. They just always read or write from the standard I/O files, the first three file descriptors. So in bash, you can change where input and output is coming from using these symbols. So the less than arrow means redirect standard in. So normally if I were to just run grep hello, why is nothing happening if I just run grep hello? Yeah. Right. Well, more than that, it's actually waiting for standard in to give it data. So it's, yes, there are no lines yet, so it hasn't output anything. But the reason the program isn't terminating is that it's waiting. It's called read on the terminal, and there's no end of file yet, so it's blocked, waiting for input. So as soon as I start typing input into the terminal, grep will start reading that in, and not until I close the file, I'm hitting Control D, will that read or the grep terminate. Grep is repeatedly calling read. Once it sees an end of file, it will end. Okay, so to redirect that, instead of coming from the terminal, I come from this my.in file. I use redirection. Yeah. Grep, I think it's like something regular expressions, maybe global regular expressions. Yeah, so the rep part, I think it means regular expressions. Yeah, but the G, I'm actually not sure. Maybe global regular expressions, I don't know. All right, questions about that homework problem? Okay, why doesn't a program have to open the standard out file? Yeah. Well, yeah, they're set up. Yeah, so they're set up, and who does that setup? So the process, like grep, doesn't have to open standard out. Who does open standard out? Bash, or whatever process is running grep. So it doesn't have to be bash. We showed examples of our own programs creating processes, but yeah, in the case of grep on the command line, it was bash. And so those files are already open when the program is running. Okay, good. What syscall duplicates file descriptors? Yeah. Yeah, dupe 2, dupe 3. These are the dupe calls. And then I just asked you to write a snippet of code that redirects a process's standard out to a file called my.out. I'll show the examples again that we went through quickly last time. But does anybody have questions about this? This is in the lecture notes, the code to do this. Yeah. Sorry, say again? Read from a directory, like a directory file? You could try to redirect it, but Bash won't let you. So it won't open a directory file. So reading and writing of directory files is done by operating system calls, operating by syscalls. They are technically files, but they're protected from writing and actually reading. So they should be read through the system. So they are files, but they're not regular files. All right, other questions on homework? Okay, let me go over. Oh wait, actually, let me do attendance first. All right, so let's wrap up from redirection last time. Go over the last two examples again. So recall that. Remember, with creating processes, there are two different function calls or different system calls for creating a new running process. The first is fork, which creates the new process, and exec, which changes which program is running in the current process. And one benefit to this is that we can, between the creation of the process and the execution of a new program, we can manipulate I/O. And so we do that here in this example for redirection, where we call fork, and in the child, we use this dup syscall, dup2 syscall, to change where standard I/O goes, and then after that, we can exec a new program. So that's the example down here, actually. So we call dup, and then we can exec a new program. All right, let me go through this program and show it running. So the way this program will work is Bash will create a process for this child exec program. Then child exec will call fork. And now we've got two processes, both running the exact same program. But for this program, what's the difference between those two versions of the running program, those two duplicates of the running program? What code will each process execute in this program on the left? So we called fork. Are they going to run the exact same code in both processes? Yeah.
One is going to run case 0, which is for the child, and then the other one will run the parent.
Okay, good. Yeah, so the only difference between these two processes is the return value of fork. Otherwise, once we call fork, we have a duplicate of the process. Same open files, same memory, state, same code, which is in memory. The only difference is the return value. And so we use a case statement, or switch case, or if statement, a conditional, which is what we always use if we want to take a different program path based on the value of a variable, like value of input. So one will execute this code, which we'll call dup and exec, and the other, the parent, will execute this code. So in the parent, we're going to get this call to print F and then exit. In the child, we're going to get a call to dup2, which is going to replace standard out with this file that we've opened. So here, we've opened a file. Where's the name of this file come from? Yeah. So no. So the name of the file, so the file being opened is in the path variable. What's the path variable being assigned to? argv. So this is the first argument on the command line. So argv is what's passed on the command line of bash. That's the file that's going to be open. So when we run this program, we can pass any file name we want. This code will open that file. And then in the child, dupe2 will replace standard out with that open file. That's how we do the redirection. So without doing this, the child process will just write to whatever standard out was when the process was created. And so here, when we call fork, what's standard out for the child at this point in the program? Yeah. Well, indirectly. So what program is running? So this program is called child exec. I run this program, child exec. So what's the standard I/O for child exec? It's bash, as you described. Let me diagram this out. So bash, when bash is running, it has the terminal as its standard out and standard in. Let's do it this way. As its standard in and standard out. So this is the out, this is the in. When it forks a new process, my child exec program, it inherits its input and output from bash. So when we call fork in child exec and create a new process, both processes inherit the I/O from its parent, which is the terminal. So let me put the, let's see if I can diagram this somewhat sensibly. So this is the child and the parent process, and they also, well, the parent process still exists. I'll just draw the child. So we have this child process, and it also has its input and output from the terminal. Questions on this diagram? So we have bash, which has its I/O from the terminal. Bash forks child exec, our program over here, that inherits the terminal I/O. And then when we call fork, we create a new child, and it also inherits the I/O from the terminal. So all three of these processes have terminal as the I/O. Question about this? Yeah.
Sorry, not about that exactly, but with open, whenever we're opening a file to write to, are we always just going to want to put that 0644?
This is the file permissions.
Yeah. So just for this class, whenever.
Oh yeah, for this class, you can just use that.
Okay.
Yeah, that just means it's readable and writable by you and readable by others.
Okay.
Yeah, you can just use that. Ask on EdStem, and I'll point you to the documentation. You can read about what these numbers mean, what they encode.
Just another thing, like a bunch of things ordered together.
Yeah, you can OR things together. Yeah, you can do it that way as well. All right, any questions on the I/O setup right now? So this is when we call fork. This is our I/O setup. We've got these three processes. They all have their I/O from term. What dupe2 does is it takes our call to dupe2 here, replaces standard out with this open file. So we've created this open file for whatever our input is. I'll just call it file. And dupe2 will take this standard out and it'll redirect standard out to the file for the child process. That's what this dupe2 call does. Questions on that? And so what kind of have to wrap your head around is that it's not the child that's doing this redirection, it's the parent. Well, okay, Let me correct that. So it is the child process doing it. That's what the dupe2 is. The parent opened the file, and it forked, and so they're the same program running, but there are two processes. And in the child redirects its output to that file. And once that's done, then we replace the running program in this process. We replace it with ls in this case. So after dupe2 redirects the output, then we have a call to exec, which execs the ls program. And so now child is running ls, and where is ls's output going to go? Is it going to go to the terminal? To the file. LS's output's going to go to the file because that's what the dupe2 call did in the process. So the process overwrote its standard out file to be this open file that we created with open. And once we run ls doesn't care what standard IO is. It's given 3 open files already by the fork call, and dupe will redirect where those IO files go. Questions on that diagrammatically? Or any questions about the flow here?
What all,
Yeah.
So I didn't understand that.
Say again?
I didn't understand that until you pointed it out, that the IO files are like separate from the program. I figured if you call
Yeah.
exec, that wipes everything, including what IO is.
Nope. Yeah. Yeah.
Outside of that.
That's right. Yeah. The only thing exec does is it replaces the memory state. So the running program and the state of your variables.
Are there any other like wild cards that are outside of just memory?
Yeah, I guess like the process ID, everything else really, everything else about the process. So open files, process ID, how long it's been running, who its parent is, everything stays the same about the process.
So you could, if you had files 3, 4, 5, 6, 7 previously, and you run exec,
You still have those open files, yeah, and that's the key thing here is that and that's kind of the key cleverness of this design is that why would you think duplicating a process would be useful ever, because you already have the process running, and why would you separate process creation from exec? And this is one of the reasons is that you can mess with IO, you can manipulate IO, you can abstract it away from program execution. So if you decouple process creation from program execution, if program execution is just picking what code to run, and the process is just telling the kernel, kind of creating a new virtual machine for that code to run on, just like what fork does, then by separating them, you can mess with all the stuff that's unrelated to the actual program code, like IO and who's running it, how it gets run. You separate all that from just the execution of the program. Then we can do these tricks. We can do redirection, we can do pipes, we can play with IO, the kernel can schedule these processes in different ways. You can even control priority of these processes, and all that is independent of the program. Remember, the program is just the sequence of instructions. And what the process provides is the illusion to the programmer that it's exclusively running on a single CPU machine, more or less, a single core, has exclusive access to the processor, and has exclusive access to the RAM. So the programmer running LS can still write programs as if it's the only process running on a machine, and all of the management of multiple processes, including IO and scheduling, priority, how long it lives for, when it starts and stops, all that is abstracted away into fork and the rest of the system features. So yeah, glad you asked that, to just reemphasize that fork duplicates the running program part, the memory, but it also duplicates all of the system stuff, like open files and process priority and things like that. All right, other questions on this setup? So let me walk through the code one more time. We start this program. We have a single process, and remember, bash is what creates this process for us, so we inherit terminal. So right now, when we're running our program here, we have the terminal as the I/O if we run it from bash. It doesn't have to be run from bash, but I'm running it from bash, so that it'll be the terminal I/O. The process, the program will call open to open whatever file was given on the command line. So now we've got, how many open files do we have in this process at this point in the program? How many open files are here after we call open? This is a subtle question, yeah. 4, yeah, good. So we have the standard I/O, 3 standard I/O files, input, output, error. And now we've opened a new file. So we have 4 open files at this point in the running program. Then we call switch, then we call fork. How many processes do we have? Or how many additional processes do we have? We have 1 additional process. This single process becomes 2 processes. They're both duplicated. Both have 4 open files. And so remember, the open file is not the file itself. It's like a pointer to the file. So both of these processes can write to the terminal through standard out, and they can write to this file. So we've got 2 processes running here. They both have the same files open. In the parent, we just print this text and then exit. In the child, however, we first call dupe2 in order to alter where standard out, what the standard out file is, so that it instead gets written out to this file we opened in the original parent process. Once that redirection, that plumbing happens, then we call exec to replace the processes currently running program with ls. And ls is written to just write to standard out. So where will its output go? It'll go to standard out, and does that go to the terminal, or does that go to this open file? It goes to the open file because we overwrote this standard out file descriptor with the file we opened originally in the program. Questions on that? Questions on this? Yeah.
So when you do exec, it keeps all the open files?
Yes, all the open files, yeah. It just replaces memory. Just replaces the program, it's called the text segment, just replaces the set of machine code instructions, starts them at the beginning, and it replaces your heap and stack.
So if you, let's say you had a completely different open file unrelated to all this, and
Yeah.
the, exec program somehow got access to the file descriptor, maybe through the argument, it would be able to, access the files
Yeah.
without having something?
It would be able to access any open files, yeah. But remember, these are running, without permissions changes, these are all running under the same user's permissions. So whatever files they have, you as the user have permission to write to, any of your processes can also write to them.
Yeah, I'm just saying, you'd be able to, interact with the file without having to call open again.
That's right. Yeah, you don't have to call open again. That's why you'll see if you look, we'll look at pipes today. It's good practice to close file descriptors that you don't need in the child. So if you had some logging in the parent, like bash is, can do logging and other stuff, it may close file descriptors. Just like here, before we call exec, it's managing the open files, the I/O for the child. It may do other things like close unnecessary file descriptors that the child doesn't need, things like that. But I don't think there's any kind of security problem here, at least from this. Well, I shouldn't say that. There always might be. But any open files you have in the parent, this could be a problem if you change permissions. If the parent is a root, has root privileges, and then you call a child that doesn't have root privileges, you could potentially end up with some problems. But yeah, they inherit all of the same open files in the child process. Question?
So where, I take it, all these file descriptors that are always going to be around no matter what, is there a separate dedicated system memory?
Yes. So the question was, is there separate memory for this data? And yes, there is. So let me bring back the diagram from the book, if I can remember which section it's in. It's right here. So this is the diagram showing the, so this is the open file table in the kernel, and then each process has a pointer to this table that keeps track of all open files across all processes. So there are 2 open files here that your process points to before calling fork. When we call fork, this table is duplicated. The table is copied. And remember, this table is not part of the program per se, because it's not part of the machine instructions in the program, but it's part of the kernel that manages the process. Yeah.
That open file table, that is somewhere in memory, and it's
Yeah.
always going to be there.
This is in kernel memory. It's always there. The kernel manages it for the lifetime of your running machine, for the lifetime of your system. Yeah. And it keeps track of all open files across all processes. So when we call fork, that's what gets this table for. There's a per process table as well that points to the open file table. This per process table gets duplicated. So it's pretty lightweight. It's just using pointers basically. You have to copy that process data, the metadata about the process. And then if you call close, so here this is an example of calling close where the parent closes Y. It's just removing that pointer. So that file is still open, because there's at least one process having it open, but the pointer is no longer there. So the kernel, once there's no more pointers to the open file table, the kernel knows that file is not going to be read to or written from, and so it can remove that from the open file table. Okay, so last questions. Any last questions on redirection? Yeah. Yeah.
To it, will things like printf still go to the original standard out because there's still only one version of it, or will it be altered?
So that was a good question. So we showed this last time. What was the name of the file? Duplicate standard out, I think. So yeah, where does I can't remember which file it was in.
Yeah, last time it was just you do to it, and then you do the original.
Yeah, so we dupe to overwriting standard out. So where does printf write to? Which file descriptor does it always write to? Standard out. And which file descriptor number is that? If you remember. It's 1. So standard in is 0, standard out is 1, standard error is 2. So whatever file, so if you can think of this table, this is like file descriptor 0, file descriptor 1, file descriptor 2. So the standard out is just a file descriptor number. It's unrelated to what file is open behind that. So whatever this entry 1 is pointing to, that's going to be where standard out goes. No matter what file that is, printf will just print to file descriptor 1. If that makes sense.
So does that just point to like cost right? It's not dupe 2, just original.
Oh, regular dupe. Regular dupe just takes the lowest available file descriptor and puts it there. Open creates that file descriptor and has it point to the same file. Dupe 2 closes whatever the second argument is, closes standard out, and then replaces standard out's open file with FDs. It takes process. I mean, you can almost like start imagining how to implement this. What dupe 2 does is if this is file descriptor 1, it closes this one, it removes it from the table, so now it's an empty entry. And then when dupe 2 is called, it just replaces this it just copies whatever data you had in your open file, say FD4, and it just copies it there. So now it points to the same open file as dupe 2 did before. So the kind of mechanics of it are a little hard to wrap your head around. But if you just remember that standard I/O is not any particular open file, it's just the first 3 file descriptors, 0, 1, and 2. And a file descriptor is just pointing to an open file. It's not the file itself. And so just because by convention, printf and all of these other utilities just always write to file descriptor 2 whenever it's doing out, or file descriptor 1 whenever it's doing output, file descriptor 2 whenever it's doing error output, this will just work because it doesn't care what's backing file descriptor 1. It just writes to it. So if you change what file descriptor 1's, that's how you can do redirection. That's how you can manipulate the I/O of a process. Okay, so that's redirection. Now let's talk about a more sophisticated use of this redirection, where redirection, or where of this duplicating file descriptors and playing with standard I/O, where redirection was used to change I/O to go to a file, or perhaps another device. Pipes allows us to redirect I/O between running processes. So just as a refresher, each process is created with standard I/O, standard in, standard out, standard error. And we kind of covered this already. Why do you have standard I/O? Abstracts away I/O decisions. Who sets standard I/O? We talked about this already. It's the parent process, controls standard I/O, controls the creation of it by just duplicating whatever its own standard I/O open files are. Which that means processes don't have to open standard I/O. They're already open when the process is created. So the challenge, so one of the nice things about processes is that they isolate running programs from each other. So if I run ls, it's not, and I have my own program and I run ls is not going to overwrite memory in my program. If I set x to be 1, no other process can change what x's value is. It's as if each process is running on its own machine. It's like it has its own physical RAM and its own physical process, and it's running by itself. That's the process abstraction. It provides that illusion to the programmer. The problem is that sometimes it's really useful to have processes communicate with each other. Sometimes you might want to be able to change x's value based on another process. And we saw examples of this. I gave you examples of this on the command line, where we could build up bigger programs, not by writing a new program, but by combining small component programs like Lego blocks, putting them together. So for instance, if I wanted to make a program that would search for files called zip or had zip in them, I wouldn't have to write a new C program to do that. I can just use 2 existing C programs. I don't have to write a single program that's going to do every possible thing that I want. Instead, I can combine, like Lego blocks, individual simple programs and build them up by allowing them to communicate with each other. And so in this case, even though these processes are totally isolated, they're running in different, they have their own memory space, their own access to the processor, through I/O, I can communicate between them. I can send data between programs through I/O. So I/O is not just about printing to the terminal, it's also about communicating between processes. And just as another aside, network programming is really just inter-process communication. The only difference to the programmer between piping or redirecting files from a process and going out using your browser to go to a server is that the processes are on different machines. So when I run Firefox here, I have a process on my machine that's running, and it's doing inter-process communication to this CS web server, the UCF CS web server, which is sitting, I think, somewhere in this building, and it's running a process that will print out my web page when Firefox communicates with it. But you could do that locally as well. You don't have to do that on separate machines. You can just use inter-process I/O between 2 processes. And because of this process abstraction, and because of I/O, the I/O abstraction, it doesn't matter that these processes are running on 2 different machines or the same machine, or going to a file, or going to a network device, or going to another program. Okay, but what we're going to learn today is piping, is where we communicate between processes on the same running machine using standard I/O, redirecting their standard I/O to each other. All right, questions about this so far? Questions about what this will do? Questions about the bash syntax here? let me just run this to make sure we're all on the same page. All right, so what should I see output when I run this command?
Anything that has zip in it.
Yeah, every file in the user bin directory that contains the string zip. So there's a surprising lot of them, right? Not just zip. And so grep, grep without additional syntax, grep looks anywhere on the line. And so these are all the programs in bin that have the word zip in it. Questions on that? So find lists all files in a directory, including its subdirectories. And grep searches or prints out lines that have a match to its pattern that you give it. Okay, so the way this worked is we ran find. It's like running each program independently. But by redirecting their I/O, they can communicate with each other. We can have grep reading the output of find. Okay, so to do this, there's actually a special syscall that will facilitate doing this. So you could certainly do this by writing to a file first, like we did in the redirection example, and then reading from that file. On bash, you could run 2 commands and use an intermediate file. What a pipe does is a pipe creates a special file in memory that allows you to read and write to it without having to create new file storage on disk. It'll all happen in memory. And so what pipe gives you is it gives you 2 file descriptors, one for the write end of the pipe and one for the read end of the pipe. So let me draw a quick diagram of what this looks like. So when you call the pipe system call, you get 2 file descriptors. You can think of it as creating this buffer in memory, and you get a file descriptor for the write end. So if we redirect any processes to this write end, data will be buffered here in the pipe, and any processes that read from that will get that data. And this is FIFO, first in, first out. This is a queue. So whatever goes in first to the pipe will be read out first. So each one of these gets a file descriptor. What's a little, so now we have to actually look at the API for this. But the way pipe passes values is in C, you can only return a single value. So the way the pipe syscall does is it returns the value through the arguments. Has anyone ever seen this style, like pass by reference in C? Has anyone seen pass by reference? All right, not many. So the arguments aren't necessarily only inputs. They can also be used for outputs. So what you do is you pass in let me show an example of this. You pass in an already allocated array. Remember, an array is just a pointer. So you pass in a pointer value, and when this function returns, this array will hold these 2 new file descriptors. So I'll show lots of examples of this to make this clear, but you're passing in an array by reference, and the pipe syscall will fill in that array for you. So it's just an alternative way to get a return value from a C function. This is used a lot in the systems world. So the return function here is used for reporting errors, basically. And then the output of the 2 new file descriptors created for the pipe is returned, so to speak, by this reference to an array. But I'll show more of the code, but I just want to get this out of the way so that I can start using the array indices, because what's a little counterintuitive about pipe is that the first element of the array is the read end of the pipe. The second element of the array is the write end of the pipe. So this will be a little confusing, or confuses me anyway. This will be a little tricky to remember, So I'm just going to notate here which is the read end and which is the write end. So FD0, if the array that pipe populates, FD1 is the write end, FD0 is the read end. Am I getting that right? Yeah, is the read end. So you get these two new file descriptors from pipe. They both use the same in-memory file, but one of them writes to that file and one of them reads from that file. Okay, so this is pipe. Gives you an in-memory buffer, and it gives you one file descriptor to write to that buffer and one file descriptor to read from that buffer. Questions on that so far? Yeah.
You just use the regular read and write functions to read from each file descriptor?
Exactly. So the question is, do you just use the regular read and write? Exactly, yes. So remember, the file abstraction doesn't matter what's underlying the file. The file abstraction just means you can read and write sequences of bytes to whatever the file is. Because remember, the file itself is just an abstraction. It's not memory. It's not storage on disk. It's not network I/O. It's just an abstraction. So you can back that abstraction with whatever you want. You could, for instance, have a little microcontroller board on a serial port, and you can write to that using you can write and read to it from read and write commands, as long as you had the device drivers for that. So this works exactly like reading and writing a file on disk or reading and writing standard I/O. So yeah, good question. That's the beauty of this abstraction, is that you can treat any I/O, any device, even virtual ones like this, like an in-memory buffer, with the same API. Okay, so that's what pipe sets up for you. So let's take a look at diagrammatically what happens when we when bash runs this pipe. Can anyone not read this? Can anyone not read this? Okay. All right, let's look at how this works. Okay, bash will create two processes. It'll create one for find, and it'll create one for grep. Now, when these two processes are created, where's their I/O go? Where does their standard I/O go to when this is created? I know, it's a redundant question. The terminal. So if bash's I/O is to the terminal, and it actually doesn't have to be. You can also redirect bash's I/O. It's to the terminal. Then these new processes will inherit that I/O. So let me draw the I/O a different color. So when these two processes are created, they'll also share the same I/O. So right now, these three processes all have the terminal as its I/O for input and output. Questions on this? Okay. So then what bash does is it creates a pipe. It calls the pipe syscall and creates this pipe that has two new file descriptors. And then that array index 1 is the write end of the pipe, array index 0 is the read end. And so remember with redirection, what we did is we created the process, and then we redirected I/O. We took that open file and we changed where standard out goes to. And then we called exec to run whatever, ls or whatever our program was. It's very similar here, where bash, before it calls exec for find and grep. So these are the processes. I should say, this is not actually the find program. This is the find process. It's not running find yet. But what it does is it calls pipe, and then it uses that dup2 syscall to take this output of find and change it so that it's the right end of the pipe, and it takes the read end of grep, the standard in of grep, and it changes it to be the read end of the pipe. So bash calls pipe to create this new special file with 2 file descriptors, and it uses dup2 to change the find process's output to be the right end of the pipe, and it uses dup2 again to change the standard in to the read end of the pipe. Then it just calls exec for find and grep and just lets them run. So bash doesn't have to do anything else. It just sets up the I/O, executes the programs, because it sets up the processes, sets up the I/O, and then just executes the programs. It doesn't have to do anything else. And because each process, the process abstraction, allows the kernel to just schedule these processes whenever it likes, they're effectively running in parallel, and they're both reading and writing from this shared pipe. And so even though find and grep don't know about each other, they don't have to do any coordination with each other, they don't know where they're reading to or writing from, it just works to have find spitting out its output to grep, all while maintaining this process abstraction, this isolation. You know, the programmer of each of these programs wrote as if they were the only program running on the machine. They wrote as if they didn't care about where standard I/O was going to. And because of the design of this system, bash can control exactly which processes get created, how they communicate with each other, and the kernel will control when they get run to make it appear as if they're all running at the same time and they're all communicating with each other in a nice coordinated fashion, but without any specific cooperation between these processes. Questions on that? Yeah.
So the file descriptors would be like somewhere inside like the bash program. So
Yeah, and remember what we just talked about. So the question is, where are these file descriptors? So just like with redirection, when we called open in the parent, the file descriptor is just an entry in a table. So when new processes are created, it's all duplicated. So if we call pipe here, and we call fork, those pipe file descriptors are all inherited by the new processes. So that's the kind of beauty of this design, is that by inheriting all file descriptors, which is pretty lightweight, they're not actually files, they're just entries in a table, we can easily set up, I should say easily, but fairly easily set up this situation because all these processes all have the same open files. And so once bash creates these processes and these processes are running, they can redirect, the bash code can redirect where these processes are reading and writing from. And so yeah, you call pipe, and I'll show the actual code, but we'll call pipe here, and then these 2 new processes will inherit those open file descriptors, just like they inherited the open file for redirection. Yeah.
Is type an ongoing process, or does it just run once to set up I/O and then stop?
So pipe is not a process at all. You can think of it as a file, as a special file. So you call pipe once. So in the same way you call open, it's like calling open. Open sets up information in the kernel and gives you a file descriptor. Once you have the file descriptor, for the programmer, it's irrelevant how read and write are implemented for that. Read and write will be different for different, depending on if it's a device or backed by file storage or backed by a pipe. But from the programmer's point of view, as long as you have a file descriptor, and you just call read and write, and you'll get data to and from it. So the pipe, so in that sense, the pipe it's ongoing in that the kernel is keeping this buffer in memory and managing it for you. But it's kind of like a new file, having a new file. Think of it like a new file on disk, except it's in memory. And you have these 2 file descriptors to read and write from it. So a pipe is not a process. It's just, think of it as it's a file. It's a file that gets created, and the kernel manages it in memory, usually. All right, other questions about this setup? Okay, let's look at a slightly more complicated example when we have 3 processes being created. Bless you. So I think I showed examples of this, but this also, you're not restricted to a single pipe. You can create as many pipes as you like. And so diagrammatically what happens here is bash will create 3 processes, one for the find program, one for grep. Now, it hasn't called exec yet, it just forks these 3 processes. And it creates 2 pipes. Creates 2 pipes and redirects the output of the find process to the input of the first pipe, redirects the output of that pipe to the input of grep, redirects the output of grep to the input of the second pipe, and redirects the input of word count from the output of the second pipe. So each of these pipe symbols corresponds to one call to pipe. So there's 3 programs, n programs. You have n minus 1 pipes. Communicate between all of them. Questions on this? Questions on this setup? Yeah.
So you're saying there's only one pipe call?
No, there's 2 pipe calls. There's 2 pipe calls. Each of these is from a separate pipe call. So you need to call pipe once to make each pipe. So however many pipe symbols you have, that's how many calls to pipe bash is making. Yeah.
Yeah, so when you have the read.
Sorry, say again? You have the what?
When you're changing the redirection into the pipe,
Yeah.
that's a dupe process that's changing standard out to the.
That's right. So the question was, using dupe. It's not a dupe, it's a dupe syscall. Using a dupe syscall to change find's output, find processes output here. So each one of these is a dupe call by the bash program.
So if you're letting dupe changing standard out to be the 6 right of the pipe, if you're doing that for both pipes, how come they don't overwrite?
Because we're doing this for 2 different pipes. Oh, wait, how come what doesn't overwrite each other? What do you?
So like, if you're changing standard out to be the right for find and grep, how does it know that? How does it not only use standard out for one?
So these are 3 different processes. They each have their own standard out. They each have their own standard out. So we create 3 new processes. They each have their own standard out, which originally is term. So it's just like here. This grep also has standard out. They each have their own standard out. They're different standard outs. So if we were to redirect grep, we could redirect this to something else. But that doesn't affect the other processes' standard out. So each process has its own open process table. It is copied originally when called fork, but it's its own process table. That's what's shown here. So if we alter that process table, open file descriptor table, then each process has their own file descriptor table. So if we call dupe in one process, that won't affect another process's file descriptor table. Okay, other questions on this? All right, let's go to the code. Let's see how to actually do this. So there's the page. Take a look at the reading. I've put the reading for tonight, I think. You could read about the pipe call. I've already shown you the man page. The man page is here. So this is how you use it. You have to create an array first. Make sure you allocate memory. You can allocate that as a local variable. Then you call pipe, passing in a reference to that array. And it will give you 2 file descriptors if it's successful. So its return value is 0 on success, otherwise -1, just like other processes. And -1 means you don't get the pipe. So we'll just do the kind of standard simple error checking that we've been doing in this class. Okay, so let's look at pipe. And I've got this code here somewhere. Okay. Let me make sure this works. All right, let me go over the code. So here's our typical C program. First thing we do, we call pipe. We call it on this array here. So we've allocated an array locally. And remember, arrays are just pointers, right? If I were to print out pipe FD, it would be a reference. Questions on arrays? You learned about arrays and references, right, in C? Okay. So pipe FD is a pointer to an integer. We pass that pointer to pipe, and if pipe is successful, we get 2 file descriptors in this array. So once pipe returns successfully, this pipe FD gives us pipe FD1, so in this case it would be pipe FD. So these would be how we access the write end and the read end from this pipe FD variable. Questions on that? Okay, so then as before, we fork, and we've got code for the child and code for the parent. Hopefully that's repetitive by now. So now we've got 2 processes running. In the parent process, we write to the pipe. This is the right end of the pipe. We write whatever argv is, we write that to the pipe. Questions on this? So it's just using the write syscall. And instead of to some file on disk, we write to the pipe. And the thing we write is whatever argv1 is. Questions on this? So we're treating the pipe just like any other file. We're writing to it. And in the child, this is the child. So if the PID is greater than 0 in the child, we read from the pipe. So we call read, but here we use the read file descriptor, the read end of the pipe. And this is some code. I think this is from, I don't know, I took it from some example. We just read 1 byte at a time from the pipe. So all this is doing is just reading over and over and over and writing to standard out each byte from the pipe. Questions on this? Well, reading from the read end of the pipe and writing to standard out. All right, and I've got some other printfs here from before and some sleeps just to like pause things a little bit. But I've got printfs for the parent and the child. Okay, let's run this program. So I'm going to call pipe and put hello as the input. What should we see printed out by this program? What do we expect to see? So we're forking. So this program, when it runs, where is its I/O? What is its I/O when I run the pipe program? Terminal. So it's the terminal. And when I fork this child, what is its I/O? Terminal, still the terminal. So this printf in the child, where's this going to go? To the terminal. And this printf in the parent, oh, sorry, the other way. Oh, I think I have this backwards. And this printf in the parent, where's this going to go? Also to the terminal. And where is argv going to be written to? Argv is written to the pipe. So we're writing to the pipe. And here in the child, we're reading from that pipe and just writing that to standard out. So if I call pipe hello, what should I see printed out? What's that? Hello to the terminal, yeah. So I'll have these printfs, and then through the pipe from the child will print out, sorry, the parent, this is the parent. From the parent, it'll print out whatever was written to the pipe. So we get these two printfs, and we get this right here of whatever was passed to the pipe. So from the output, it doesn't look very, very impressive, right? Because it's just all printing to standard out. But this hello actually came from, it was written by the parent here, or written by the child here. This is supposed to be child. It was written by the child to the pipe, but it was the parent that wrote it to standard out. So the child did not write this to standard out. The parent wrote it to standard out. Questions on this? So this is just illustrating the use of pipe with read and write. Yeah?
You said you were reading from the pipe on like pipe-wise basis.
On a what noise?
Like you were reading it pipe by pipe? Or
Yeah.
something like that?
Yeah.
Is there a reason for that? Or is it just dramatic?
No, it's just easy. You don't have to manage. Like we don't have to. I don't know. I just took this example, I think, from the book. It's just an easy way to do it because you don't need to make a buffer. You can just. Actually, I did make a buffer. Where's my buffer? I have a single character buffer. I don't need to manage. You don't have to do it a byte at a time. This is just kind of wasteful but easy to write. So yeah, we're reading from the pipe into this buffer and then writing that buffer out. Okay, so that illustrates creating a pipe and communicating between two processes using that pipe. So remember, each of these branches of the if statement, they're running in different processes because we called fork and we tested the return value of fork. So that these are running in different processes, but I've written to the pipe some data from one process and I've read it in the other process and written it out. So I've successfully communicated between two processes, even though they're isolated. I've used I/O through files to read and write between processes. Okay, let me show this in combination with exec. So this is where the kind of more interesting process I/O emerges. So if I want to, then I can use this facility to set up the pipe and then exec different programs. And because of standard I/O, I can redirect standard input and output so that one output from one process will flow to the input of another process. Okay, so let me walk through the setup and the kind of algorithm and pseudocode before I show the actual code. So there'll be 3 processes total. So just like in this diagram here, there'll be 3 processes. The master process, as I'm calling this, bash in this case, or my program, it'll create the pipe. It'll fork each program, redirect the standard I/O of each process to the pipe, and then exec the 2 programs. So this is what the algorithm looks like. In our program, we'll create the pipe. We'll fork a process for one program of the pipe and use dupe2 to replace that process's standard out, and then call exec to run that program. We'll also fork a new process for the write program and replace its standard in with the pipe, and then call exec on that program. And in the parent process or the master process, we'll just wait for these to finish. And I already showed this diagram. This is the diagram of it. So in this case, bash creates the 2 processes, redirects their I/O to the pipe, and then calls exec to actually start these running programs. Questions so far? Questions on the diagram, what we're going to do here? All right, let me show the code. I've got a program called pipe exec. So this program will run the pipe that we ran on bash before, where we're going to run find, and we're going to run grep, and we're going to redirect the I/O between them. So let me go through the code. We call pipe to create the pipe. Then we call fork to create the process for the find program. And here is the code that runs in the child process. So we close the read end because we don't need the read end. Sort of optional, but it's cleaner to do this. And here, this is where we're doing the redirection to the pipe. We're taking the pipe's right end and we're replacing standard out with that right end. So it's just like in redirection. So remember, in redirection, we opened a new file on disk with the open command call and then replace standard I/O with it. Instead, here, we're replacing standard I/O with the pipe. Questions on that? Does that make sense? So yeah.
Oh, when you say right, you mean like right on the piece of paper, not like the right side.
Yeah. That's another confusion about this is I diagram this on the left side. The input end of the pipe, the in end of the pipe. So this is the in end of the pipe, and you just reference the manual to like get it right. But just think of this as we're setting the standard out of this new process because we created a new process here with fork, and then we're changing standard out to be the pipe instead. We're using the input end of that pipe. And then we call exec. So now find is running with its standard out going to the pipe. So created a new process, overwrote standard out to be the pipe, and then started running find. Now, we checked the PID to see if we were in the parent or the child. If we were in the child, we ran exec, and exec is not supposed to return if it's successful. When we're in the parent, we do nothing. Instead, we continue on and fork another process for the right child. For the right-hand child, for the grep process. And we do the same thing. When we're in the child, we redirect the input of that right-hand child to be from the pipe. And then once it's redirected, we call exec for grep. So let me diagram this with the right names here. So our pipe exec program, first called pipe, to create this new pipe, and then it forked a new process which will be used for the find program. And for this new process, it called dupe to redirect the output of that process to the input of the pipe. Then it called exec to run the find program. So now we've got this new process here whose output is to the pipe and will be running the find program. After that, or during that really, the pipe exec program calls fork again, and then calls dupe to redirect the input of the fork from the pipe. After that's done, we call exec on grep. So these are the dupe2 calls. So these are our three processes. Each process has been redirected, or the two processes have been redirected to the pipe, and that's it. And then we just let them run. Questions on the setup? Questions on the setup again? Any other questions? So this is what this code on the left does. All right, so in the parent, so there's a lot of closes here to kind of clean up open file descriptors. The program will still operate as expected. And then we just call wait, which just leaves the parent running until the processes have finished. But the main meat of this is in this algorithm here. Create the pipe, fork a process for the left-hand program, replace it standard out with the pipe and run it with exec, fork a process for the right-hand program, replace it standard in with the pipe and run it, and then wait. That's it, right? That's the algorithm. Simple algorithm, but a lot of C code to run it. Okay, so let's. There's pseudocode here if you want to take a look at it, but let's run this actual code and see if we get what we expect. So we ran this on the. We ran this with Bash, and what we got was this list of programs that have zip in them. So we should expect to see the same thing when we run this pipe exec program. And we do. We get the same output. So we've done the same thing that Bash is doing, but we're using the actual syscalls that Bash is using. Questions on this? Yeah.
Is it just like how I guess like kernel manages the file? Because you print out the file descriptors, right? Or the right.
Yeah.
And it just so happens that like standard is.
No, so remember, standard I/O is always 0, 1, and 2. So 0 is always standard in. So this is the dupe 2 call here. So if we have dupe 2, the pipe's input end is file descriptor 4. Its output end is file descriptor 3. But 0 and 1 are always standard in and standard out. So this is redirecting standard out, and this is redirecting standard in. I think it should be right and left pipe. This is actually the left pipe. But does that answer your question? So standard I/O is always 0, 1, and 2. So what dupe does is it just replaces 0, 1, and 2, or whatever file descriptor you want, with another one. So 3, whatever 3 was pointing to, which is the pipe, 0 will now also point to the pipe. Is there another? I thought there was another question. Other questions on this? Yeah. Oh, okay. That's just a feature of grep. So grep has a feature. We could pass a flag to grep to do this if we wanted. So grep just has a feature to do color. So you can turn on color for grep. It's just extra characters that go to your terminal, and your terminal interpret those and presents them in color. Other questions? Yeah.
Yeah, and the second time you initialize the new process, the second time you call for it.
Yeah.
So what if the first process you created also run this?
Oh, okay. So the question is, we created a child process, and we call fork again later in the program. But remember, we called exec on that child process. So exec will replace the running program. Exec will never return if it's correct. But if it does return, we've got this exit in here. So no matter what, for the first fork, the process will end on this line of code or earlier, and will never go to the second fork. Other questions on this? All right, so there's piping. There's homework 12, and I'll see you next time.